Есть звук. Есть звук.
Да.
Спасибо. Так, ну хорошо. Okay. Is it working now? It is. Well, let's begin. Better late than never. Volodya, could you write your email on a piece of paper and pass it on? So we'll collect the names and the emails of those who are present, and then I'll check with the Learning and Teaching Office to see if they have any more emails of the people who follow the course online, and then we'll arrange for a few extra classes to compensate for those classes which we didn't have in the beginning of the term. Anyway, we continue studying cohomology of elliptic complexes, and today last week we saw an example of an elliptic complex which calculates the cohomology groups of a coherent sheaf over a complex analytic manifold. Now we'll see some other applications. In particular, we'll see the signature operator, and the interest of this operator is that this operator, the index of this operator, is the signature. And we'll also prove the Serre duality theorem for coherent sheaves. And what does, by the way, for those of you who are taking or have taken a course in algebraic geometry, what does the theorem say?
Duality, perfect fading between two spaces.
The Serre duality. Suppose we have a complex algebraic variety, smooth and compact or proper, and a vector bundle. The Serre duality theorem says that we have an isomorphism of this type, and basically we know how to interpret both the right-hand side and the left-hand side in terms of the cohomology of elliptic complexes. So all we need is to find an isomorphism. And this isomorphism is given by the Hodge star. Okay, so this was an advertisement. So now let's get to work. So first of all, let's recall the Hodge star from linear algebra. So suppose we have a finite dimensional vector space over R equipped with a scalar product. Thank you. Then there is a Hodge star operator. Let's call the dimension n. Then there is a map from the pth power, from the pth exterior power to the n minus pth exterior power, such that okay. Let's see. So such that W1 for all W1, W2 inside lambda p, we have this this identity. In other words, the star operator reduces taking the scalar product to taking the wedge product. To wit, W1 wedge the star of W2 is the scalar product which is induced by the scalar product on V times the volume form. Now, what is the volume form? Well, there are several ways to define it, and can anyone suggest at least one? Say again?
If you have a metric, if you assign a metric on our space, we can define the one who gives us one and the q and the unit q.
Okay, so one way to define the volume form is to say that the value of this form on an orthogonal basis of V should be 1 or minus 1 depending on whether okay, now if we have just a vector space, we have no preferred positive frame. So it makes sense to say that it makes sense to talk about orthogonal frames. Okay, I take any orthogonal frame and I define vol by requiring that the value on this frame should be 1 or minus 1. Okay. Well, this statement is linear algebra, and it's not very difficult to prove. So let's skip it. Okay. Now, but before we move on, we need some more information from linear algebra. Which is again not very hard to check directly. The square of the star is not the identity. It's plus or minus identity. And in particular, we have minus 1 to p n minus p on lambda p. Again. I encourage everyone to check it, because sometimes I make mistakes with formulas of this type. So don't take my word on it, check it.
Can you remind what is the scalar product here?
This one. Again, there are several ways to define the scalar product, but there's a straightforward one. We basically take any orthogonal frame in V, and then we take all exterior products of the elements of this frame, and we declare the result to be an orthogonal frame in lambda p. And once we have an orthogonal frame, we are able to define the scalar product of any two vectors.
Actually, it is just the ground determinant of the vectors on the composable elements.
The ground determinant. What do I mean? The ground determinant of what?
Not gram, but so the scalar product of V1 wedge and so on, wedge Vn and W1 wedge so on Wn is just the determinant of the matrix Vi with Wj, the dot product of this.
You're probably right. Although I didn't. It doesn't matter. The scalar product will be some determinant. Let's. Yes, and it's not very easy. It's not very difficult to write this determinant explicitly. Let's. Okay, I agree with this. Let's move on. Okay, do we need anything else? We'll see. For a smooth manifold, a smooth we can do the same fiber-wise, and we get a Hodge-Star operator from lambda p t x to lambda n minus b. We get the Hodge-Star operator from p forms to n minus b forms, which squares to minus 1 to some power. Yes, this star operator is an automorphism, and so is the other one. And let's see. So we can extend the we can extend this operator to an operator between the complexified exterior powers just by linearity, and we'll shortly see why we need to complexify. Okay.
I think here we need to say that x is readable.
Here. Let's see. We need. Okay. Yes. We need this vol to make sense for each over each x. So we need to have a global volume form, which basically means that the manifold is orientable. So let's assume this. Okay. Now. Now let's remember that we have the Durham operator, and using the star operator, we're able to write the conjugate of the Durham operator. Okay. Now, if n is even, then the conjugate of d is minus star d star. Why on earth is this true, and how to check it? Well, let's think. Well, let's at least try to check this formula, and we'll probably get into some sign troubles along the way, but at least let's give it a try. Okay, now
Sorry, but what is there?
d upper star is the conjugate operator. We have a scalar product on the forms. So we have a scalar product on P forms and another one on P+1 forms. All those are induced by the scalar product on by the metric, basically. Okay, so using the scalar product, we can define the scalar product.
What is the scalar product of P forms?
There's two ways to look at it. The simplest one would be to say that we just take a frame, an orthogonal frame in V, and then we say that the resulting monomials from lambda p are orthogonal.
Okay, and then we have function and we integrate it using volume form, right?
Yes. Okay, so this is what happens fiber-wise. And then I integrate the resulting function against the volume form. Or alternatively, I could use this this formula. I only need to replace W's with omegas. And then all I need to integrate is W1 wedge star omega 2. And this is what we will do shortly to check this formula. Okay, so let's okay. I want to calculate the conjugate of D. D goes from lambda p to lambda p+1. Okay, so the conjugate will go to lambda p+1 to lambda p. Okay, so I take omega.
Omega 1 from global sections of this.
Omega 1 is a smooth global section of. Sorry. This is bad notation. Let me fix it. So we take this is. This one is slightly better. So we take this bundle and we take a smooth section of this vector bundle. And so it's the same with omega 2. Okay, now and now we want to check the following thing. We want to check that the integral of uh, d omega 1 wedge star omega 2. Okay, let me explain where this came from. So this is the same as the scalar product of d omega 1 and omega 2. And we need to check that the result is the same as the integral of omega 1, and then I substitute this expression. So I put a minus outside, and okay, d star omega 2. Okay, now does everyone agree? Why do I want to check this? Because this is the same as omega 1. Scalar with omega 2. Okay. Let's see if this works out. Okay, I already know what the double star is. Double star is -1. I assume that n is even, because otherwise the sign will be messy, and we won't need it. It's not massively difficult, but it's messy. Let's not get into this. In other words, we need to check -1. Okay, I have -1 here, and this double star squares to what? Well, it squares to p n minus p, but n is even, so the result is the same as -1 to the p.
No, it's not p and n minus p.
And what is it?
So, omega 2
Sorry.
omega 2 is p plus 1 form. Then we apply Hodge star. We get n minus p minus 1 form. Then we apply differential. Oh, it's okay.
Yes, let's. But you're right. Let's check it again. So this double star is something we apply to this form. So this is a p+1 form. The star is n minus p minus 1 form, and the d is n minus p form. Which makes sense. So the result is an n minus p form, and okay. So let's write n minus p instead of p, although the results are the same. Okay. So we have this, and let's put this minus 1 outside. We get n minus p plus 1, okay? And then what do we have? We have omega 1 wedge d star omega 2. Okay, so we need to check this this formula. How do we check this formula? Well, there is not much choice. We need to use the Stokes theorem, which says that the, well, what do I have? I have omega 2 omega 1 wedge star omega 2 is 0 by the Stokes theorem. Why? Well, because this is a p form, this is a p plus 1 form. The star is n minus p minus 1 form. No, I got confused again. Okay, so this one has a degree. This one has degree p plus 1. This one has degree n minus p minus 1. Okay, so this is p. Okay, so yes. Okay, so this thing is sorry. I started thinking in the wrong direction. This is an n minus 1 form. But it's when we take the differential, the integral is 0. This is the Stokes theorem. Okay, now let's try to remember the Leibniz formula. So d omega 1 wedge omega 2 plus minus 1 to the p omega 1 wedge d star omega 2. Okay. Well, let's see. So this is this, and this is minus this. Why? Because the dimension of the dimension n is even. So we basically get the formula we're after. Okay. Now,
It also showed
Yes, we need we need oriented and compact. Yes. Yes, exactly. Because otherwise, there's there could be a problem with this integral. It might diverge. Okay. Well, let's use this formula to deduce a few things. Well, this was lemma 1. Let's say lemma 2. Let's check that the Hodge star operator anti-commutes or commutes, we'll see which one, with the Hodge Laplacian. Okay, I will erase. I will erase this part. So lemma 2. By the way, does anyone remember which one it is? Commutes, anti-commutes. We'll see. So we have star delta. Again, assuming assuming the dimension of x even. Okay. Is it plus? Is it minus? Well, let's put a minus here, and we can always change it for a plus afterwards. So the point of this is that star takes harmonic forms to harmonic forms, which we will prove once we have this identity. Well, what do we want to check? We want to check that star d d star plus d star d is minus d star d star d star. Okay, so this is the formula we need to check. Okay, let's check it. I use the formula for d star, which were just obtained in lemma 1. Okay, I have a d star everywhere, so I can forget about the minus. So what do I have? Star d star d star. Plus star d star, no, double star, d Okay. Minus d star d star star minus star d star d star. Okay, very, very nice. Mhm. Okay.
Okay, we're gonna
Shapes all wavelengths. So.
лучше без минус.
Yes, yes, it looks okay, but hold on. So, well, whichever sign we have here is plus or minus. Okay, so yes, so let's replace minus by plus. It wasn't very hard. Okay. Now, what do we have? Well, if we do this, then these two terms go away, and these two terms are equal. Why? Well, because on lambda p, this thing is minus 1 to the p n minus p, and okay, here we first apply d, and we get a p plus 1 form, then n minus p minus 1 form. Then we get an n minus p form, and then we apply omega star, so we get basically the same answer, n minus p times p. Okay, so the results are the same. Well, as a consequence or corollary, we have the Poincaré duality theorem. We have the Poincaré duality theorem, which says that the pth real cohomology vector space of X is isomorphic to the n minus pth one. And well, here we have an isomorphism. Why? Because we have a metric, and the isomorphism is as follows. We use the fact that this is HP, and this is Hn minus P, and we use the star to identify these two vector spaces, where HP is the kernel of the Laplacian intersected with omega p of X. So we use the fact that the star operator takes harmonic forms to harmonic forms, and this is something which we proved a few weeks ago. It's basically part of the main theorem about elliptic complexes. Every cohomology class of an elliptic complex has a unique harmonic representative. Now this is this is a very basic form of the Poincare duality theorem, because there are many more general versions of it, but still, well, it's something. Okay, let's now see whether we have time. Do we have? We have 2 more minutes. Okay, well, no, do we? Okay, anyway. Let's now try to remember what the signature is. Does everyone remember the definition of the signature? Well, let's start with a finite dimensional Euclidean vector space. And suppose we have a quadratic form on this vector space. We all know that this quadratic form in some basis can be written as a sum of squares and then a sum of minus squares. Is everyone familiar with this theorem? Okay, and the index is the sum of the pluses minus the sum of the minuses.
What about zeros?
Yes, so now let's generalize this to manifolds. The signature of a manifold is the signature of the intersection form on the middle cohomology. What does this mean? Well, for odd-dimensional manifolds, there is no middle cohomology. Okay, so So the signature of a manifold is 0 if the dimension is not a multiple of 4. Okay, so if the dimension is not a multiple of 4, then we just, by definition, set the signature to be 0. If the dimension is a multiple of 4, then we consider the intersection form on the middle cohomology, where L is 1/2 n. So if n is divisible by 4, then this form is symmetric. If n is divisible by 2 but not by 4, the form is antisymmetric. And if n is not divisible by 2 at all, then there is no middle cohomology. Does this make sense? For example, the intersection form for curves on a two-dimensional manifold is antisymmetric. But the intersection form for surfaces in a four-dimensional manifold is symmetric. Okay, does this make sense? Значит, формы пересечения. Значит, на нечетно-мерных многообразиях ее просто не на чем рассматривать. На четно-мерных многообразиях, но такие, что размеры делятся на 4, она нечетная, поэтому она не интересная. Ну, все нечетные невыраженные формы, то есть все антисимметричные невыраженные формы изоморфны. А вот если размеры делятся на 4, то появляется что-то интересное. Именно в форме пересечения, значит, там значит, над R появляется сколько-то плюсов, сколько-то минусов. И вот там сигнатура вот этой формы будет сигнатура многообразия. By definition. Okay. Now, we want to calculate to identify the signature with the index of some elliptic operator. Okay, let me denote the signature by sigma. And we will use the de Rham operator as our elliptic operator. But there's a problem. The de Rham operator is not the de Rham, de Rham plus the de Rham conjugate. Well, the problem with this operator is self-conjugate. So it doesn't have an index. Well, it does, but the index is 0. So the trick is to choose to use the same operator, but choose different bundles. And here we need complexification. So we need to complexify the tangent bundles and their exterior powers. So let's assume that the manifold has been equipped with a metric. And then, as then I basically consider the complexified version of the star operator. So far nothing happens, I just take the star operator and complexify it in a straightforward way. And using this operator, I want to construct another one which is almost the same up to multiplication by a complex number. Okay. Okay. Again, let's assume that n is even. Okay. Now, where this formula looks completely arbitrary. Where does it come from? Okay. Okay, I take I to some strange power, and then apply the complexified Hodge star. Okay, where does this expression come from? By the way, it might be wrong. But what do I want? I want alpha squared to be the identity, not just plus or minus identity, the identity. Well, it's not very hard to see why such an expression indeed exists. I have lambda. Sorry, I have star c. Star c squares to either 1 or minus 1. Well, if it already squares to 1, I don't do anything. If it squares to minus 1, I need to multiply by some power of I, and then the result will square to 1. And to what power? Well, here is an attempt. Okay, do we want to check that this expression works? Значит, мы хотим, чтобы в квадрате было не плюс-минус 1, а просто 1. Значит, что делать? Если оно уже и так 1, да, и причем 1 или минус 1 зависит от того, какой степени формы. Если 1, то ничего не делаем. Если минус 1, то значит, нужно умножить на и в какой-то степени. В какой степени? Ну вот утверждает, что в такой. А вот, значит, ну, я не знаю, хотим, ну, то есть, мне кажется, что она подходит, но, значит, все-таки, значит, мои утверждения нужно проверять. Вот хотим ли мы это проверить? Хорошо, но в любом случае мы там, значит, ну, в общем, даже если это, вот это не подходит, какая-нибудь еще подходит.
Понятно, что всегда можно подобрать.
Хорошо, значит, окей, let's Uh, okay, I suggest we have a short break until 10 past 6, and then we'll decide whether or not we want to check that this that this alpha squares indeed to 1. Okay, are there any questions? Значит, зачем мы это сейчас делаем? Значит, смотрите, мы хотим, да, у нас есть сигнатура. Yes, well, it looks like it's working. Okay, well, let's continue. Yes. Do we want to check that this works? Well, actually, we only need to know this this exponent for the middle dimension. Let me see. Okay, so. And I do remember the answer for the middle dimension. So let's see if this. Example. I only need 2 examples. Example 1, n 2 divides n. But 4 does not divide n. And then I get I to the power and p is 1/2 n. Okay, so then I get what? Then I get 1/2 n, 1/2 n minus 1 plus 1/2 n. And what do I get? I get I to the, well, I get minus 1/2 plus 1/2, which is 0, so I get n squared by 4. And if n is divisible by 2 but not by 4, well, for example, 2, I get 4 by 4. So the result is I, just I. Does everyone agree? And a second example, 4 divides n, and again p is n divided by 2. So this seems to work, and if 4 divides p, and p 4 divides n, and p is n by 2, then what do I get? I get well, I get again I to the power n squared by 4, but this time I have 4 squared here, and 4 squared cancels 4, so I get 1. And this is all I need, as we shall see. when n is divisible by if n is divisible by 4, then this whole thing gives 1, which is what I'm supposed to get.
But when we apply this alpha twice,
when we apply twice, we get 1. Again, this is something that needs to be checked, and we can check it if we want to, but this this is always reassuring, but not necessarily illuminating. But the idea is to insert some factor here, so that the square is not just plus or minus 1 depending on the degree, but always 1. Okay. Now, now I want to define two vector subbundles. Subbundles of what? Subbundles of the exterior algebra of the cotangent bundle, complexified. And these, fiber-wise, these correspond to the eigenvalues plus and minus 1 of alpha. Now, the question is of course, why what we get are vector bundles and not just random collections of vector subspaces. Let's see. Well, to see this, we need to remember a few things about principal bundles and induced bundles. Do these words ring a bell? Not really. Okay. Now, okay. Let's talk about that. We will need both principal and induced bundles in the future.
So now for each fiber, we take the ideal space, we take either 1 or minus 1, and then we want to check that we obtain a vector bundle.
Yes.
This sounds like something technical.
Yes, but the idea is the idea is to avoid those complications by using induced bundles. But first, we need to know what these are. Basically, let's start with a topological with a topological structure group. Suppose we have a group which acts continuously on a space X, on a space F. Now, if we have a group acting on a space, we can define a fiber bundle with a structure group structure group G and fiber F. Basically, the description is self-explanatory. We require that all fibers should be homeomorphic to F, and all gluing maps should take values in G. What's a gluing map? Suppose we have a neighborhood U and a neighborhood V, and the preimage of U is identified with U cross F, and the preimage of V is identified with V cross F. So over U intersected V, we get two ways of identifying the preimage with F, and we require that there is, we require that the transformation of F, which transforms one identification with the standard F with the other, should belong to G. Actually, while we're at it, let me state this more. Because there are several possible versions, and
The identification should be G invariant.
no, it should belong to G. Okay, so so I have U cross F, and I have V cross F, where U, V are open subsets, and
What is X?
X is topological space.
Any?
Yes. We will shortly use our X instead of this X, but for this definition we don't need any other assumptions, just a space. So we have U. If we have such an identification, if we have two U and V, then we we get a map from U intersected V cross F to itself, which is a homeomorphism and it's given by xy inside U intersected V cross F goes to x fx of y, where fx of y is a homeomorphism which depends on is a self homeomorphism of f, which depends on x. Now there are several versions. Let's state those. There are several versions, but yes, we want this to be an element of G, meaning we want to have a function from U intersected V to G such that the map fx for all x in U intersected V should be given by gx. And we want this function to be continuous. Now, Now, if all spaces involved are Hausdorff locally compact, then a locally trivial fiber bundle is the same as a fiber bundle with the structure group being the group of the homeomorphisms of the fiber. And maybe in so. So in this case, a local trivial bundle is the same as a fiber bundle. Equal to the group of all homeomorphisms of F. And in general, this is not quite true, but I don't think we'll have any encounter examples where this poses a real problem. Although who knows? Anyway. So basically, we require that all glowing functions for the bundle should take values in G. Now, a principal bundle is a fiber bundle with a structure group with a structure group and fiber being the same. And the action the action is by left translations, and this is important. Okay, so basically we just use G as a model for the fiber. Now, the reason principal bundles are called principal is that they induce all other bundles. What does this mean? Well, this means if we have a principal G bundle and F if F is a G space, then we can form okay. Now I haven't. Okay, I haven't explained one important thing yet. So let's forget about this this part. I need to explain one other way to view principal bundles. Now let's see. Let's remember that each group acts on itself on the left and on the right. So if I have a principal G bundle, I have a free right action of G on P. How do I get it? Well, I use this description, and I use the standard right action of G. Let's say I use G for F, and I use the standard right action of G on itself, and left and right, the actions by left and right translations commute. So the right actions on each individual U cross G glue together to give a single well-defined right action of G on the whole of P. Does this make sense? And the quotient space with the quotient topology is just X. Why? Well, because the action is the action of G on itself by right translations is transitive, meaning we can translate any element to any other element. And the map into the quotient is a local trivial bundle. Well, which basically follows from the fact that when we use G for F and quotient out the G, we get just U. And conversely, if G acts freely on the right, on a space P, such that the map into the quotient is a locally trivial fiber bundle. Then well, let me say a little vaguely, P can be given the structure of a principal G bundle over X equal PG. We'll mainly need the first implication. If I have a principal G bundle, I have a free right action. Now I'm able to define this this thing, the induced bundle. Okay. Now, what is the induced bundle? Well, I basically take the quotient with respect to the following action of G. Suppose I have G inside G, and I want to apply it to X and Y, and the result is X G, G minus 1 of Y. Here, in order for this to make sense, I need G to act on F on the left, and the result is the right action of G, and I'm allowed to take the quotient and I call this the induced bundle. The idea of the induced bundle, we use the same we use the same gluing maps for this bundle as for the principal bundle. But this time they act on F. Well, let's consider a few examples. Examples. If F is Rn and G is GLN, then the bundles with fiber F and structure group G are precisely real vector bundles. And the same applies if I replace R by C. Now, so this this allows one to so this this construction gives one, starting from a principal G bundle, with structure group G and fiber F. Now the question is, do all fiber bundles with structure group G and fiber F come from a principal bundle? And the answer is, if the action of G on F is faithful, then yes. Otherwise, not necessarily. Okay, now faithful meaning the kernel of the action is trivial. For example, GLN R acts faithfully on Rn. So all vector bundles come from principal GLN bundles, and the same for GLNC and so on. Okay, let me write this down. All vector bundles with structure group G and fiber F can be obtained in this way if the action of G on F is faithful. Which happens, for example, in this case. Okay, now we have this example and the complex analog. Let's see. What about bundles with a metric? And by the way, okay, let's before we move on to bundles with a metric, let's look at this example, and let's see how one can construct a principal bundle starting from a vector bundle. Okay, I'll erase this part. Suppose I have a real vector bundle, and I sort of know what a real vector bundle is. Now, where do I get a principal bundle? Can anyone venture a guess?
We need a principal bundle for GLN.
Yes. So suppose I have E X, a real vector bundle. I want a principal GLN of rank n. And I want a principal GLN bundle.
We can just consider E of GLN, the classifying space, not as one of classifying space.
Yes, but it's another bundle. It's a principal bundle, but it's another bundle.
You want to construct a principal bundle for GLN?
I want to construct a principal bundle starting from a vector bundle. How do I do this? So what do I do with where do I get P?
Maybe we can take endomorphism.
Endomorphisms. In a sense, yes, but endomorphisms is not quite what we're after. What we're after are n-frames. What is an n-frame? If I have a vector space, then an n-frame in this vector space is of dimension n. Then an n-frame in this vector space is simply an ordered basis. Okay. Now. It's pretty straightforward how to construct a similar thing for vector bundles. I just take the set of all m tuples such that all the elements of the tuples are in the same fiber of the vector bundle, and they are linearly independent. In other words, they form a frame. Okay, so this is not very complicated. Now, where do I get the right action? Well, obviously, GLN of R acts on n frames. In any, if I have a vector space, then I know how to calculate I know how to apply an element of GLN of R to any frame. I don't need a preferred frame. This is very important. If I have just any frame, I apply an element of GLN of R, and I obtain another frame. What's the recipe? The recipe is very simple. Suppose I have a matrix, and suppose I have a frame, V1, etc., Vn. And then I forget that those V1, etc., Vn are vectors. I treat them as numbers. And then I multiply row by column, as one usually does. And then we get a column of linear combinations of V1, etc., Vn, and this column is another frame. So basically the problem is that this is a left action, but one can transform it into a right action and vice versa. So it's not really a problem. Anyway, is this example clear to everyone, or isn't it? let me just add that n frames in the same fiber of E. Otherwise, it doesn't really make sense to talk about frames. Okay.
So is it an open subset in the word with one null code?
Yes. There's one. Hold on. There's one thing. The endomorphism bundle has a section of the identity. Now, this thing does not in general have a section. Okay, so yeah, so here's the difference. Suppose you have a vector space. Well, if you have a frame in a vector space, this doesn't give you an endomorphism or an automorphism. To get an automorphism, you need another frame.
So if we have sections, then we have frames. Identify it with automorphisms.
Yes, but it rarely happens. Yes, if we have a section of, but then it rarely happens because if there is just one section of a principal bundle, then the bundle itself is trivial. And we basically we use the free write action to construct an isomorphism between the trivial bundle and the bundle with a section. Okay, so in this example, the passage from a vector bundle to the corresponding principal bundle is straightforward. Okay, let's see what we have. Later on, we'll need to talk some more about about bundles with a structure group because we will need to define a reduction of the structure group. But let's not talk about this at the moment. Let's just see how one gets. How one gets bundles vector bundles with a metric from principal bundles. Namely, suppose E over X is a vector bundle with a metric. Then my claim is E is P O vector bundle of rank n. Now, since the metric is the same, we can choose transition maps to be to take values in the orthogonal group when we glue a vector bundle with a metric starting from multiple copies of a neighborhood of a base cross the Euclidean space Rn. Okay, again, how do we get this where PON is is a principal O(n) bundle. So what do we do? PON is in fact is the bundle of orthogonal, not just any n frames, orthogonal n frames in the same fiber of V. And the rest is very similar to this example. There is a right action of ON on orthogonal frames and so on and so forth. Now, the point of this is this construction makes it quite straightforward to define various functors, such as the exterior power or something else. So let's see. So. An oriented vector bundle vector bundle with a metric can be obtained in the same way by using SO instead of O. Okay, now I think this is more or less all we need. Why? Well, let's remember why we started talking about this. If I have a real space with a metric, I can construct an operator alpha from the complexified exterior algebra to itself, complexified. Using the same formula we used for differential forms, namely alpha is I to some power times the star. Both ingredients make sense. Okay, now alpha squares to 1, same as for forms. Okay, so inside V we have the eigenspaces which correspond to the eigenvalues 1 and -1. And then I use the associated bundle construction. I have the tangent bundle Tx, or okay, not the tangent. Let me take the cotangent bundle Tx. I know that it comes from well, I know two things. I know it is oriented. That's what I assume, and I know that it's a vector bundle. So Tx is B S-O-N over S-O-N. Rn, sorry. Okay. Now, I use the standard metric on Rn to define the star product, the Hodge star. And then complexify, I define alpha. and I get two standard subspaces, V plus and V minus for V equal Rn, and then I use this, and those are SON submodules or subspaces. They're both preserved by SON. So I use the same principal bundle, but this time I use the action of SON on V plus and V minus, and I get two vector bundles.
Why SON acts on V plus and V minus?
Well, let's see. So, let's remember what the definition of alpha is. Alpha is something times the Hodge star, and the Hodge star is defined using the same metric we use to define SON. And it's linear algebra to check that alpha okay. It's linear algebra to check that the eigenspaces of alpha are orthogonal. Okay, so the Hodge star is an orthogonal map. Okay, now the Hodge star on without complexifying. Okay, now
Complexify something.
well,
by time, then we take complex eigenspaces, and then we take their real parts, right?
No. We keep them complex. Those are those. Okay. No. Sorry. Sorry. You're right. So this thing. Hold on. No. This thing, of course, is all wrong. They're inside lambda v times c, and lambda v times c. Thank you. So yeah, so this was a mistake. These same as alpha acts on this space. These are subspaces of lambda v times c. And okay, let's just say I can't think of a two-line proof. Let's say it's an exercise in linear algebra.
Okay, now it's almost clear.
Okay, so the reason is the reason this is the reason this is less painful than checking something directly is that we use the same principal bundle for all vector bundles, but different representations of SON. What else? Okay, now we want to, so we know this already. What do we want? We want to see whether or not alpha commutes with with the Laplacian. Okay, now
What is Laplacian?
well, the Laplacian is the complexified Laplacian.
So now we are in situation of manifold, not linear.
Yes, yes. Now we well, all this was all this intermission was to explain why lambda plus and lambda minus are subbundles and not just random collections of vector subspaces.
They are also lambda plus.
Yes. They're SON subbundles.
Are SON subbundles vector subbundles?
Well, since V plus and V minus are vector subspaces, when we apply the associated bundle construction, we get vector subbundles. Okay, now let's see. So alpha. We saw that the star commutes with the Laplacian. So alpha commutes with the Laplacian as well. Well, because it's a scalar multiple of the star.
The only problem is sign.
Yes. So here I think I'm supposed to have a minus because I would want alpha to interchange pluses and minuses. But the result I get is a plus. Which is strange. Sorry?
Why do we get plus?
Where do we get plus? Because the relation commutes with the star without the minus.
So this multiplication by I is the same on both sides, right?
Yes. Yes, this factor is the same. Let's see. The relation preserves the degree, so the factor is the same. Okay, well, it follows from this formula, or from the same formula with a minus, that alpha preserves harmonic forms, but it's normally supposed to interchange the pluses and the minuses, meaning it's supposed to interchange harmonic forms which are here with harmonic forms which are in the other bundle. Okay, maybe we did something wrong earlier, and I need to think about this. Meaning, mainly, maybe there was a mistake in the formula for the star operator.
I don't understand what should interchange here, plus and minus forms.
Alpha. Alpha should take forms here, forms in lambda plus to forms in lambda minus, and vice versa.
Why?
Well, because that's
No, alpha on plus forms, it acts as identity, right?
yes.
So it
Hold on. Yes. Yes. It's. Hold on. Of course, yes. It's a eigenspace. Eigenspaces don't change. Now, okay. So let's see. Okay, now we have constructed we have constructed two bundles, and what we're looking for at the moment is is an operator which not necessarily alpha. In fact, the operator will be another one. It will have okay. We're looking for an operator which interchanges lambda plus and lambda minus, or more precisely, takes sections of lambda plus to sections of lambda minus, and vice versa. Okay, let's see. So what's this operator? Well, let's.
Maybe you want the greater the operation.
Well, the Laplacian, no, but let's try d plus d star. Okay, so this is d minus star d star, and maybe I want this operator to anti-commute with alpha. Let's see if it works. So alpha is star times something. Star times, well, let me call this I to the power, let me call this, I don't know, epsilon p, where p stands for the degree of the forms. Okay, so I have epsilon p star, which is alpha, d minus star d star d star. I need to check whether or not it's the same as d minus star d star, and then this is what I want to check. Here, okay, if I apply alpha d minus d alpha, okay, so okay. What does this operator do? So here we have two factors which go in two opposite directions. Brilliant. Okay.
Why there is no star operator?
Because I haven't finished writing yet. Okay, now let's look at this. Let's first look at this part. We have d, and we have this star d star, and they go in the opposite directions. D increases the degree, and this one decreases the degree. So when we apply star, when we want to apply alpha afterwards, we have to use different exponents here for different epsilons. It's a mess. Okay, so let's state this as a conjecture or question, and we'll where d is d plus d star. And maybe there is an easy way to handle it, but I need to think about that. Okay, so the plan is next time we'll finish the proof that there is an operator which I suspect will be D, this one, which takes sections of lambda plus to sections of lambda minus and vice versa, and the index of this operator will be the signature of the manifold. Okay, are there any questions? Okay, well then this is it, and I will send an email about having an extra class or 2 or 3 or several.
Вы